Yeah, so good afternoon. Good afternoon, Sessions Chairman, and also everyone over here. So the it's an interesting work which I've done over here along with our team from Jadavpur University, Kolkata. It is the regression-based EGCG detection in green tea employing MIP electrodes. So tea is an important beverage and very essential beverage, we all know. And when it's tea is something which everyone likes the most. Now nowadays people are mainly shifting towards green tea because of its benefits and all. And why we are working on this particular area is because this the EGCG content. EGCG is basically nothing but the epigallocatechin 3 gallate. It's just a chemical composition which is present in green tea. Okay, and this is basically responsible for all the benefits which comes with green tea. Now we are going to check that the quality of green tea using this MIP electrodes. So here we'll be coming with the introduction, based then with the experimentation, flow of work, feature engineering, data analysis techniques, results, and the conclusion. Now, as I already mentioned, that green tea is one of the important and the healthy beverage, right? And I also mentioned about the EGCG. What EGCG is basically what, and it's basically for its important benefits. I've already mentioned about it. Now, coming to the sensor which I've created, it is basically an MIP sensor. It's molecular imprint polymer sensor. Now, this molecular imprint polymer sensor, it will have the capability to sense only the ECG content present in tea when it's dipped into the tea sample. Now, when we have received the data set, okay, we have received the data set from that. Then once the data set is recorded, then we have applied state-of-the-art algorithms. Mainly the tree-based modeling has been done, like decision tree, random forest, XGBoost, AdaBoost, gradient boost. Okay, so and based on that, we have done the performance metrics has been checked to evaluate the performance of the model. We have so for the experimentation part now, we have considered the tea from different region of India, where we are having 16 different tea samples. And when we have performed this MIP based technique which we have applied on this data set, we got a feature of 80 features. Okay, we have got 80 features, and also we have done 5 repetitions on each tea samples. So if we say about the sample size, as we are having 16 T samples with 5 repeated runs, so it is giving me the total 80 samples. And each sample is giving a feature of 80 features. So it is giving a data size of 80 cross 80. Now coming to the flow of work. So in the coming to the flow of work, first there is the 3 electrode system. 3 electrode system. One is the reference electrode, that is the EGCG electrode, along with that one counter electrode, platinum, and this working electrode. This working electrode is basically nothing but the MIP electrode, which we have considered in this scenario. Now, it will give the current value. As I mentioned, it will give you a feature of 80 cross 80. Okay, now based on that, the data pre-processing has been done, statistical has been applied. Post that, the this feature engineering has been done. Okay, like box of transformation and the feature extraction by polynomials has been done, the tree-based modeling, and based on that we are running multiple tree-based algorithm, and then we are finally coming up with the best algorithm which work better for our data set. Now coming to the feature engineering, first of all, I told we have done box plot transformation. Now why box plot transformation? When we have seen 80 features, then we have saw the skewed, how the data is skewed among the features. Then we just consider those features which are having skewness greater than 0.5. Okay, for that we have performed the box plot transformation, and once we have done it, so we check the value of the box plot with lambda, which we normally call it's a 0.15, and box plot is a powerful power transformation. Okay, and where we basically the box was done on out of 80 features, we have done on 67 out of it. Then we have checked the correlation coefficients from the here on the 80 attributes. Then we are able to see that the majority of them are negatively correlated. Further, to make the model a little bit more linear, so we have considered the features based on polynomials. Okay, so there what we have done, we have taken the square root cubic term and the square root terms, and then the number of features 80, it increased to 230. Now coming to the data analysis technique which we have done, the first standardization has been done, where we are basically making it normal distributed value. Now we split the data set of say 70 cross 30 ratio, 7:3 ratio, where out of 70% of the data has been taken for training purpose, 30% for the testing purpose. For the training and the validation part, we have done the cross fold of 10K fold. Then the training has been performed on the cross 10 fold validation, and the tree-based modeling has been performed. As I mentioned earlier, it's the decision tree, random forest data boost, gradient boost, XGBoost, and then further, the model was tested, okay, on the remaining 30% which was left, okay, and then we have considered the regression metrics, basically, which are the error terms along with the coefficient of determination. And here we can see the for one of them, like the XGBoost one, how we are able to see over here the error. Okay, so how the residual plot is there. Then we are having the prediction plot is there, and the actual versus prediction plot is there. And this is the one we have kept because out of multiple models, XGBoost performed best in this scenario. Now, coming to the results section, if I go a little bit deeper, so for each of the model, we have done some hyperparameter tuning. For each of the places, we have done hyperparameter tuning in these scenarios. Okay, and we have done hyperparameter, takes a maximum mini, and we have done this grid search in this scenario. And then based on the K fold, we just 10 times, and then we run that model. And based on that, we have taken the best model out of it. So similarly, we are having the search space and hyperparameters used for each of the modeling techniques. Now over here, we can also see the time taken for each of the models, okay, to execute. Here in the table 2, we can see the actual versus how the prediction performance metrics perform. Now, if you see the errors, right? If you see the error terms, the errors are very much less for XGBoost, and the R square value, which is basically it's almost able to predict almost 99%. So that's really good. And also, if we see the actual versus the prediction one, it is all very close. So based on that, we can definitely say that the variance trade-off is maintained. And now in this chart, we can definitely see the one is the time taken, and also the prediction accuracy, how the prediction accuracy flown, and how the time taken for it. Now here we are able to see that the data boost is taking a lot of the time, and this Adam was taking a lot of the time, whereas the if we see random for and the XGBoost is taking less time, and this if we see XGBoost is taking almost half of the random forest time, okay, and whereas the XGBoost is giving almost 99.6% of accuracy, we can say. We have also done some comparative study with the existing literature. So here, when we have used this NIR spectroscopy, it gave us this prediction accuracy of 94.9%. This Raman spectroscopy gave 82%. Whereas when we are using this low cost MIP electrochemical sensor on the which we have developed, so it is giving almost 99.62% accuracy. So just to have a concluding remarks, the EGCG has been considered, in the green tea, that is having a very good health benefits. The tree-based regression methods that has been used, okay, is in this case on the molecular lipid polymer, we have considered the tree-based regression algorithms. We have taken the response based on the TPV, and we have used the ensemble learning techniques, and where we have used the bagging as well as the boosting one, bagging for random forest and the boosting for the XGBoost, where we have also seen that boosting performs better than the bagging one in this scenario. And also we have seen, and we from the metrics, okay, we have almost able to say that 99% of the ECG content is can be determined very easily by with the XGBoost algorithm. And similar type of approach, right? Similar type of method can be deployed for other quantitative determination of other components present in TIA or any other sector as well. So these are some of the references. Thank you.